All right, here's question 5 and question 6. Let's start with number 5. So they give you this function, and in part A, they ask you to show that this is dy dx. So in other words, they are giving you the function, they are telling you what the answer is for the implicit differentiation, and just asking you to show that that's what the answer is. So here's the work for that. There's the original function. So we're going to take anything with the derivative of y, we're going to write a dy dx. Here's your product rule. And then let's group everything with the dy dx together. And then divide to get dy dx by itself. And what do you know? It's the answer that they said it was. So that's part A. It's just asking you to show the implicit differentiation. They're telling you what the answer is. They're just asking you to get to it. Part B, they asked you to write the equation of the tangent line. And they gave you the point 0 square root of 3. So there's your, we have y minus y coordinate equals the slope times x minus the x coordinate. And they gave you the x and y coordinates, so you just need to find the slope. How do we find the slope? Well, we plug it into dy dx. So plug in 0 for x, plug in square root of 3 for y. The nice thing that happens there, cosine of 0 is 1, sine of 0 is 0. The nice thing that happens here is that the square root of 3's cancel, and I just get 1/4. So there's y minus your y coordinate equals my slope, which I got from plugging into the derivative, times x minus your x coordinate. Part C. In part C, they asked you to find where the tangent line is horizontal. So the tangent line is horizontal where dy dx is 0. Tangent line is horizontal where dy dx is 0, because horizontal line has a slope of 0. So we need to figure out where the derivative is 0. Y times cosine of x is 0. First of all, y could be 0, but we're going to rule that out. The reason we're going to rule that out is because the problem says when x is from 0 to pi and when y is greater than 0. So they don't want us to factor in y being 0. They want us to use x equaling pi over 2. And then we take that and plug it in to the function because it asks us for the coordinates. So when x is pi over 2, plug that back into here to get the y coordinate. So you should put a pi over 2 in for x, figure out what y is. That takes a little bit of messing around with that equation, but not too much, to get the y coordinate. Then for part D, determine whether f has a relative minimum, relative maximum, or neither at the point found in part C. So basically what we're doing is a sign chart analysis here. We found that point in part C where the derivative was 0. So we already know the derivative is 0. So we need to know is f prime changing from negative to positive, from positive to negative, or is it not changing at all? So what I'm going to do to test that is that I'm going to plug in the endpoints. So we're analyzing from 0 to pi. What is dy dx doing? Well, at 0 and at pi, y is square root of 3. You can plug in to the original function and find that. At 0 square root of 3, we already figured out what dy dx was. We did that in part B. And then at pi square root of 3, at the other endpoint, dy dx is negative 1/4. Because now instead of the cosine of 0 on the top, we've got the cosine of pi, which is negative 1. So it's all the same as we did in part B, except the cosine ended up being negative. So we get a negative 1/4. So that means it was positive to the left and negative to the right. So we are changing from positive to negative. That means we have a maximum at pi over 2. All right, moving on to number 6. So this has a couple tricky parts to it, but also a couple parts that should have been pretty doable. So first of all, a portion of the slope field is given. Sketch the solution curve at the point 0, 0. Your solution curve should not go above this kind of horizontal line of the slope field. We have it going up, and then it's going less up. We're basically, playing a connect the dots, connect the lines here. That's what your solution curve should look like, roughly. What your solution curve should look like. Then for part B, using correct units, interpret the statement of the limit as t approaches infinity. We'll come back to that. I want to jump to part C and say use separation of variables. And another clue that you're using separation of variables here is that it's talking about the particular solution. If you see that phrasing, then you should know that you're doing separation of variables. If it asks, find the particular solution, then it's asking you to do separation of variables. I see some people look at that phrasing of the question and then put a big question mark because they don't know what to do. It's a separation of variables question. So, part B, the limit as x approaches infinity of a of t, or as t approaches infinity is 12, means that there's a horizontal asymptote, right? Limit out to infinity is 12. That means that we approach 12, but we never get there. That means that that's kind of the maximum capacity of medication, because that's what the y-coordinate is. The y-coordinate is the amount of medication that's in the person's system. And so, that is the maximum capacity of the medication. That theoretically, over an infinite amount of time, that's how much medication would be in the patient. That's what the limit means in the context of that question. And then they ask you to do a separation of variables. So first of all, separate out the variables. I'm going to divide by 12 minus y. I'm going to move the dt over to this side. Then let's take the integral of both sides. Antiderivative of 12 minus y. This negative is out here because of the chain rule. Undoing the chain rule. Absolute value there. So I went ahead and rewrote it. I got the negative over to the other side. I rewrote it with the exponential. And then brought the c out underneath the exponent, because this is e to the negative 1/3 t times e to the c, which means we can bring the c out in front. I also added the 12 to the other side, right? Because I could subtract it and then multiply by -1, and the -1 times constant is still a constant. So that process is just solving for y. This piece is getting y by itself. Then plug in our point, which is that when t is 0, then a of t is 0. So plug in 0, 0, and that means -12 is my coordinate for c. So a -12 goes out in front of the e to the negative 1/3 t. And then part D, a different procedure is being used to administer medication. So we have a new equation. At t equals 1, there's 2.5 milligrams of medication in the second patient. So that means that y is 2.5 and t is 1, and it's asking, is the rate of change of the amount of medication in the second patient increasing or decreasing? So is the rate of change increasing or decreasing? That means if we're asking if a rate of change is increasing or decreasing, we're asking about the rate of change of the rate of change. So that means this is a question about the second derivative. So if it asks about whether a rate of change is increasing or decreasing, that's a question about the second derivative. So we need to take the second derivative, which involves the quotient rule. Derivative of 3 is 0, and then minus that. Low d high minus high d low over the square of what's below. And then we're going to plug in, first of all, that dy dt should be 13 over 6. We can plug in our points there and figure that out. And through that, plugging in all of our coordinates, we figure out that the second derivative is negative at that point. So that means that the rate of change is decreasing at the point. All right, so those are the first two I asked you to do. We'll go over the rest another time.